If I understand correctly, your buckling was discussed with you in the stress analysis course in the last week or second last week or something like that. Because and they didn't spend more than maybe a week, more than a week, or more than 3, 4 lectures on it. Because this is a complicated thing. It's just to give you a flavor of stuff. Okay, and the only thing that you analyzed actually was the buckling of a beam. Okay, under very special conditions. So here, the situation is this. So I have a beam here. It doesn't have to be, usually it's called column. If it's like that column, it's like this is a beam. I have a column here. If you apply force here, if you apply force, by the way it is right now, it looks like this is simple support and this is simple support. The way I'm trying to do that, right? Just look. Angle changes there, angle changes here. And this is simple support. Okay. If I compress on this, if this was a perfectly uniform, homogeneous beam, and the load was applied, exactly at the centroid, this will compress. That's it. It will compress. In real life, if you just press on it, this will compress. Not in real life. In theory, it just compress. And you can compress it in principle all the way this height. I mean, it's so garbage, but you can do that. But in real life, when this load reaches a certain value, suddenly it snaps. Okay, that's called the buckling load. When the load reaches that value, this snaps. This is the buckling load. And the theory says if you increase that load, for example, if Dr. Green told you 1,000 pounds for this geometry, if you make 1,001 pound, it goes back to where it was. That doesn't happen in real life. Okay, when it buckles, you increase the load, gets more and more, and eventually it fails. Now, that is why they say this Euler buckling load that you got there, and I've written it here, is a non-conservative estimate. Non-conservative estimate. What does non-conservative mean? When I say this is a non-conservative estimate of calculating the buckling load, what does it mean in layperson's terminology? Yeah. Okay, worst case, fine, but I want a layperson's, layman's way of saying it. This is non-conservative value. That means be afraid. This will actually buckle before that load. Before Dr. Green's value of 1,000 pounds, maybe at 50 pounds, it will buckle. Don't worry about bigger than 1,000. Okay, but it could be anything below that. Non-conservative means that. That means danger. I mean, if you want an upper bound, this is good. Fine. But not real life. Now, the other thing is that it depends, this buckling load from stress analysis class depends on the end conditions. Notice that there are different end conditions there. The one which says K equal to 1 is the simply supported one, the one that I have here. That's the third one from the right. Simple support, simple support. That formula is perfect for K equal to 1. Simple support. But if it's anything else, the value of K has to be modified. Okay. These formulas are theoretical, and you might say, well, they don't match reality. Yeah, but these things you need to know, okay? Because sometimes you don't have to go a finite element analysis to do these things. Sometimes you do. For example, in the case of a rocket, your SAE rocket project, anybody's going to join that? Accelerating. The shells of the rocket may buckle. If you accelerate too much, it compresses the shells too much. And when you compress, they take a can of Coke and try to compress it, it will buckle. So those things you can't get out of these formulas. Okay? But you can always get, for example, the first very rough estimate, pretend that the bucket is a beam with a hollow cross section. With a tube, it has an I, it has an A and everything, so you get an upper bound. So these are important, but you've got to be careful. Now, the other thing is that never use buckling, never use planes of symmetry in buckling also. Because if you say, for example, this is a plane of symmetry, it is. This is a plane of symmetry. It cannot buckle like that. Whereas it could. It's going to be a much higher load to make it buckle like this. But if you insist that this is a plane of symmetry, it never come off the plane. So just like you ignore, you may skip some frequencies for vibration. If you do planes of symmetry for buckling, you will miss some buckling modes and loads. Okay. However, going against my own advice in this problem, I don't know, chapter whatever it is, chapter 23, I'm going to use plane of symmetry. It's just that I'm saying that I know there's a problem. Don't use it, but I'll use it. The actual problem that we're doing is something like this. Yeah, that is the frame that we want to analyze. So we have a square frame, and I took it, compress it on both sides laterally, like this. You might say, okay, if I accept the fact that buckling symmetry will be used by me, well, I can take only a quarter of it, right? Bad idea, but I will do it. Quarter of it, clamp. And you think about this, when you think about it, I want you to visualize how this thing buckles. This end is clamped, and that end is, that top is clamped. When you look at this vertical piece, which is half of that, when you think about it, it's this situation. So this vertical piece is like this problem. The bottom is clamped, the top is clamped, and I'm pushing it down by that force P. Okay? And you can find the buckling load based on those things, Euler buckling load. You can do that. You can do it based on these, and I've done it. I've done it down here. Okay? But the situation, and I want to find out what that value is. Okay? What that value is. What the buckling load is. Now remember, you might look at the one on the right and say, okay, so what is that? Is the P? Is that P unknown, or is this P unknown? It's the same thing. It's just that looking at it like that is applying the load in the lateral direction, taking that and looking at it like this. Pythagorean theorem is that basically we have two beams that are under compression of load P. The magnitude of that load P is square root of P squared plus P squared, which is square root of 2P. These two problems are the same. That's what I'm saying, except for the fact that I'm using symmetry. I should not be using. Even in the thickness direction, I'm using symmetry. I'm cutting it through that frame. The whole thing is, that thing is 1 inch deep into the board. I'm taking half of it. Bad idea, because you are throwing away some buckling loads. Okay. Yep. So we're going to take half the thickness. You see that? Half the thickness, bad idea. And the back is in the surface slider because I'm taking half of it. The bottom is on surface slider because I'm taking half of it. And so is the side on the right. Okay, let's go ahead and do that. Any questions here? Okay, so let's go start with a part file. All right, on a convenient plane, on that vertical plane, I will sketch. (10" by 10". Clean it up in a minute. Okay, so dimension, let's make this in 10. Let's make this thing 10. Okay, let's make this thing 1 inch. And this thing 1 inch. Good. Exit. And against my own advice, I'm taking half of the thickness, which is 0.5. So pad that by 0.5. Good. Apply material to it. It's made out of steel. On this part. All right, good. Now we're going to go to generative structure analysis. You might say, okay, wait a minute, I've got two options here. One is a static analysis, the other one is dynamic frequency. Okay, so what is the buckling thinking? Well, the first step to do any buckling analysis, the first step is doing a static analysis. So any software, the first thing that you do is you do a static analysis. So static is default right now. You say, okay, let's apply our restraints and loads. So surface slider on the back, on that face, there it is. See that? That surface slider is on the entire back. And I can mix them up or I can do them separately. It doesn't matter. It's on this face and the bottom. If there is any confusion, possibility of any confusion or mistake, let's do it separately. There we are. And there we are. Okay. Now, I have my restraints and I'm doing a static analysis. No more the buckle. Static analysis. I'm going to put 1 pound dummy load downward on the top edge and 1 pound dummy load on that same edge to the right. Or to the right. Dummy load, 1 pound. So force, distributed force on that edge in the direction x minus 1. Wait a minute. What is this direction? Direction. Let me do direction y, horizontal one first. Let's change this thing. Horizontal one. 1. Does that look good? Yeah, good. Okay. Pointing to the right. As it's supposed to. Right there. You can see that. Point to the right. And 1 pound dummy load down. Say okay. Another one. On that edge. In the direction Z, 1 pound dummy load. I'll put a minus because I want to compress it. It really doesn't matter. You can put a plus 2. But don't worry about that right now. I can do both of them going the other way around. It doesn't matter. Both of them coming in, both of them going out. Okay? All right. This is it. We can run it. No word of buckling. There is no buckling. Mention of buckling at all. Static analysis. I put the surface sliders. I put the 1 pound dummy load in the 2 directions. No word about buckling. And this is the same in any software. And this is the usual message that you get. Remember the message about rotation, blah, blah, blah. Don't worry about it. Okay, question. I want to ask you a question. This is a static problem that I did. 1 pound dummy load. How would the shape of this thing look like? How would it look like? Just use your common sense. You see the restraint. You see the load that I'm applying to this part. How would it look like? Do you have an answer? No? This is not magic. This is not a trick question. How would it look like? Let me ask you this. I apply 1 pound dummy load. How would it look like? 1 pound. No. If I applied axially, If I applied axially, yeah, compression. It'll go down. I'm doing the same way. Here, look at the plot. No big deal. That's the way it's supposed to be. Yeah, it's compression. Good. It cannot come off the plane, okay, because of the surface slider that I put up there, etc. Good. So what is the buckling stuff here? You didn't do any buckling. And you're absolutely right. There's no mention of buckling. It's a static case. The usual stuff that you have done in the last 2 weeks. So now you're going to go insert buckling case. Insert buckling case. It needs a static solution before you can actually do buckling. You'll see why. Because when I say insert buckling case, let me undo this, try it again. I think I put something else. I didn't say buckling case. I must have said something else. Let's see. Insert, I think I did the combined case. Buckling case. Look, it says, where's your static solution? Right there. See that? This thing opened up. It says, where is your static solution? The one that I just did. It's asking for it. So I go and select it from the tree. Right there. See that? You see here it says, where is the static solution? I go and select it from the tree. And I say, okay. Didn't complain. Now we're going to run. Good. Let me deactivate this plot. This plot is from the static one. I'm going to deactivate it. And I'm going to get my new plots. Click on it. If you double click on this plot, let's do that. Let me double click on this plot. Again, we have occurrence tab. Occurrence tab. Remember, occurrence tab was for frequencies before. Now it says occurrence tab. These are the load multipliers. The very first number says 29,000. In other words, take your dummy load, multiply it by 29,000. That's your Euler buckling load. That's your buckling load. So if I apply to this frame 29,000 this way, 29,000 this way, because I put one pound on it. 29,000, 29,000. So the magnitude of that square root of 2, Pythagorean theorem, square root of 2, 29,000, that is your buckling load. And somebody caught me off guard on the first lecture and said something. What I'm telling you, these are multipliers. I'll come to that guy's comment in a minute. What about these? These are the other buckling load. Multiply that 1 pound by whatever. What is it? 123,000. 123,000 this way, 120,000 this way, it will buckle. But remember, I said that the first one is the problem. If it buckles on the first one, you would not go to the second one and the third one, etc. So those are all theoretical stuff. These other buckling loads are all theoretical. Theory says, Dr. Green said, if you apply that much, it will buckle. If you make the load bigger, it will not buckle. Go back to the original shape. I mean, you know, this is not going to happen. But the moral of the story is that it's the first one that's important, and it's going to buckle like that. And visualize this thing 4 times. It buckles like the top goes like this, the bottom goes like that, the vertical edges bend inward. It looks like this. As I said, somebody caught me off guard. I was very happy this morning and said, don't you have to multiply this thing by 2? In other words, I put one pound dummy load. This is the buckling load multiplier, the load multiplier. So take my 1 pound, multiply by 29,000. Do we have to multiply this thing by 2? Why is that? The backside that we didn't model. The backside that we didn't model. So actually the buckling load is double of this. If I had not used planar symmetry, I would have got double this value. Right in that table, would have got double this. I was